Welcome back to our very last chapter of the year. It is time for chapter 16, Standing Waves and Interference. Here we go. Okay, so we're going to start with this idea of superposition. And superposition is where two waves pass through each other, and as they pass through each other, they add together when they're in the same position. So here's a little example of superposition. We have wave number one right here, and then we have wave number two right here, and they are each moving towards each other. So they're moving towards each other. When they come together, you'll notice that wave number one has an amplitude of what I'll call 1, and wave number two has an amplitude of what I'll call 1. And then when they overlap, they have an amplitude of 1 plus 1 for an amplitude of 2. So you can see that when they're overlapping, they add together and get bigger. And then they pass through each other and continue on their ways. So now the red wave, wave 1, is moving off to the right, and the yellow wave, wave 2, is moving off to the left. Okay, now this can be either constructive or destructive interference. So constructive is when they add together in a positive way and make a wave bigger. So here we have two waves, wave over here and wave over here. There's a triangle and a rectangle shape on those waves. They come together at 1 meter per second. So at time 0 seconds, they're 2 meters away. At time 1 second, they've come right next to each other. Time 2 seconds, they're now on top of each other. And so the triangle right here is on top of the rectangle right there. Then when they get slightly askew, half the triangle is still on top, and then the other half down here is below. If you add those together, you get the original triangle. And then they pass fully through each other and they continue on their way. So that's constructive because they build up together. Destructive interference is when they work against each other. So here you have two waves, but one of them has a negative amplitude. So the negative amplitude one right down here in red, when they come together and they add together, they overlap. And so here, this section right there and right there are overlapping each other. And so they end up kind of canceling each other out. Here, they are fully canceled. So you would have them right there and right there. But in practice, you just have no visible anything. So I would draw that as the straight blue line, although the waves technically would be positive and negative. They're just fully canceling out. So, I mean, technically it's a straight line, right? You would see it as no energy for that split second. And then they pass through each other and continue again on their way. You'll notice that the one that was positive at the beginning up here, moving to the right, is still positive, still moving to the right, but now it's further off to the right. So they've passed through each other. All right, so that's constructive and destructive interference. Let's think that through, looking at two pulses on a string. So stop and think. Two pulses on a string are approaching each other at 1 meter per second. What's the shape of the string at time equals 6 seconds? So this is time equals 0 seconds. And I'm going to just pay attention to that peak right there and that peak right there, because that's the highest point, and that's easier for me to keep track of. So if it's 6 seconds at 1 meter per second, 2 plus 6 would put my peak right here. So I'm just going to kind of draw it. There's my peak right there, and it'd be down like that. And then this one is at 18, and it's going this direction. So minus 6 would put it at 12. That would put my peak there. Boom. And then this one goes 2 to 6. So here, that's a difference of 4. So it'd go down to 12 like that. And this one would go the opposite direction down to 8. But now these parts right here, this bit and this bit would add together. So it would actually go like up a little bit and then back down. Because right here, that point there has this value plus that value. So that's like 1 and 1 has to make 2. So I need a point all the way up there. So my end goal, it would look something like this. And that would be D. And D is centered around 10. And it goes vertically. And it has my 2 high points on the ends, but then a higher point where the middles have added together. Okay. So when I have waves that are consistent, I can create a standing wave. So a standing wave is where you have crests and troughs are stationary in the same places as the 2 waves have superposition with each other. So here's kind of an example of a standing wave. I have 2 sinusoidal waves, 2 sine waves moving towards each other. I've got a set of 3 crests and a set of 3 crests. And as they move towards each other, they overlap. So this is showing the overlap. One wave is the red wave. One wave is the orange wave. And if you add their positions together at all times, you end up with the blue set. So the blue set is kind of tough to see. It's curling through here, but that's the blue. And then when they overlap at 1/8 of the period, they reach maximum amplitude. And you can keep doing this all the way through. There's a point at 3/8 amplitude where they create pure destructive interference. And so when you put all those together, you end up with this position over here in C. All right, so here you can see that they go through, and if you just track the blue dot goes to maximum low, 0, medium high, maximum high, medium high, and then back to 0. And then continues around and around and around. So we end up with this kind of motion up and down and up and down and up and down in a single point. Now, when you put that all together and show kind of what it looks like, you end up with a standing wave that looks like this, where you have areas that are always like a bump kind of thing and areas that never move. So that area that never moved would be on this previous one right there, right? That point always stays at neutral all the way through. So that point that stays at neutral all the way through ends up becoming that point right there, which we call a node. Okay, a node is an area that stays at neutral the entire time. The antinode is the area that's moving. And that's the part that I'm going to call like a hump or a bump. So in this case, I see nodes and antinodes. Now remember that a full wave has 1 crest and 1 trough. So that would be 1 full wave in yellow. And you realize that is 2 antinodes, 2 bumps. So 1 full wavelength to right there is 2 bumps. So half of a wavelength is 1 bump. Since 2 bumps is 1 wavelength, half of a wavelength, or wavelength over 2, is 1 bump right here. So the nodes and the antinodes are each spaced half of a wavelength apart, the antinodes being the bump part, and the nodes being the neutral part is still. Okay. All right. Getting a notice that the speaker may or may not be working, so hopefully that is plugged in and working. That'll be fine. All right. So when I compare this and look at the intensity, you'll see that for the intensity, the area that are antinodes right here have really high intensity because they're moving up and down a lot. The areas that are nodes have 0 intensity because they're not doing any motion, which kind of makes sense. All right, so let's do a little stop and think. A standing wave is set up on a string. A series of snapshots of the wave are superimposed to produce the diagram at right. What is the wavelength? Okay, So in this case, I see 3 bumps. So that would be 3 half wavelengths, or thought of another way, there's 1 full wave there. So if this whole thing is 3 meters and that takes 3 bumps, then 2 bumps would be 2 meters. So that would be a total wavelength of 2 meters. If I wanted to use an equation, I could say 3 meters equals 3 halves of a wavelength. And then to get wavelength by itself, I could multiply by 2/3, multiply by 2/3. The 3's cancel and get me a 2. So wavelength equals 2 meters. Although I just kind of think about it logically, if 3 meters is 3 bumps, then 2 bumps is 2 meters. All right. So reflection. When a wave reflects, or where it bounces off of a boundary, we could see this where a wave is going, say, off a mirror. We could see it when it's transitioning between materials, so like air to water. That could be a point of reflection, or air to glass could be a point of reflection, or it could be a string bouncing off of a wall. In this case, the string appears to be tied on to the wall right here. So the wave comes in positive. You can see it's up here, has a positive amplitude. And then once it bounces, it goes back at the exact same speed. The size of the arrow is the same, so same velocity, but now it is inverted. So it has the negative amplitude. When it hits a boundary and bounces back, it's a negative amplitude. Now, sometimes we get situations where we don't have pure reflection. We have a little bit of reflection and a little bit continuing through, like light hitting water, air to water, or light hitting glass. I can kind of see my reflection in the glass, but I can also see through the glass to whatever's outside. So when that happens, we see partial reflection, a partial bounce back, and a partial continuation in the new medium. So here I have a positive wave, positive amplitude, going along on a thick rope. When it hits that transfer right here, it continues along the small medium, and then part of it bounces back, but with a slower wave speed. Now, when I have it on a thin rope coming in with a positive amplitude, part of it continues on, but not as large. And the reflected pulse will come back as an inverted. It's a reflection, so it'll bounce back with an inverted negative amplitude. All right, so why do we talk about reflection? We talk about reflection because reflections cause standing waves. As waves bounce back and forth, they get reflected between the two boundaries. So basically you have two tied ends or two closed ends on your wave. And so the wave just bounces back and forth between those two ends. So here we show that you send 2 waves, and those waves are going there and then another one there, and they bounce back and forth between these 2 tied ends. We would say that the length of the string, the distance there, is going to be L, the length, and the reflected waves bounce back and forth. So when we do that, we can indicate that these are different modes. So when you have a standing wave, you can talk about them as which mode it is. Really, it's just talking about how many humps there are, right? How many bumps do I see? So the simple one would be a single bump, 1 up or 1 down. And that's mode number 1, M equals 1. And that's 1 antinode or 1 hump. In this case, the total length there, right, L equals 1/2 of the wavelength. If I have 2 humps, then I'd go up and down. That's a full wavelength. So that's mode 2. and that's L equals 1 wavelength. Okay, mode 2, 2 antinodes. With 3, L equals 3/2 wavelengths, or 1.5 wavelengths, and that's mode 3, 3 antinodes. So if I try to put an equation to that and match it, I could say the wavelength of M is equal to 2L divided by the number of modes. So the wavelength, basically I'm just taking this equation here and inverting it, right? Multiply 2/3 by both sides, and I get wavelength equals 2/3 L, or 2L divided by the number of modes, which is 3. Then, if I wanted to solve for the frequency of each of these, I could remember my core equation, which is wave speed equals wavelength times frequency. Solve it for frequency. So the frequency of a certain mode is equal to the wave speed divided by the wavelength. Plug in for the wavelength, and that is the modes, number of modes, times the velocity, the wave speed, over 2L. So that's just a manipulation of this equation and this equation, saying now frequency equals mv over 2L. I got to be perfectly honest, memorizing these equations is not helpful for me. I just always, always, always start with this guy. If I start with this one and I remember 2 bumps is a wavelength, you're good to go. Okay. So let's do a little bit of look at standing waves. So possible standing wave modes of a string fixed at both ends. And I've got different equations here. The mode number is equal to the number of antinodes. All right, so let's do a stop and think. A 2-meter long string carries a standing wave as in the figure at right. Extend the pattern and the formulas shown in figure 1613 to determine the mode number and the wavelength of this particular standing wave mode. Okay, so the easy part is the mode number. That's just the number of bumps. So that would be 1, 2, 3, 4, 5. So mode has to be equal to 5. That would give me D or C. And now the question is, what is the wavelength? So I know that it's 2 meters total, and every 2 bumps is a wavelength. So that is 1 wavelength. So that's 2/5 of the total, right? 2 out of 5 bumps equals 2 meters. So 2/5 of 2 meters has to be equal to the wavelength. That is 4/5, which is 0.8. So that would be C. The wavelengths is 0.8 meters, and the mode is 5 bumps, 5 antinodes. I guess I should use the technical term. All right, so we can use this idea of standing waves to talk about fundamental frequencies. So fundamental frequencies, we also can call harmonics, and the fundamental frequency is the standing wave that's mode 1. So mode 1 would be this guy right here, and it could be at any of these positions: high, medium, 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 or low. I guess neutral is somewhere in there. So this one is the fundamental frequency, and it's F1. We know it's the fundamental frequency because it's the first option, the single antinode, where the length is going to be equal to half of the wavelength. So 2 times the length is going to be equal to the wavelength. And I can solve for that with the fundamental frequency is equal to the wave speed divided by 2L. That's, again, a manipulation of that core equation. V, or F, is equal to wave speed over wavelength, and then plug in that L equals 1/2 wavelength into here. Actually, it's that manipulation of it going into there. So F1 as mode 1 would be the wave speed over 2L. Then, if I wanted to figure out frequency 2, I could just multiply F1 by 2, because now I have 2 bumps, right? 1, 2. If I wanted to find the third frequency for 3 bumps, I could multiply F1 by 3. 4 is 4 times F1. So whatever the number is, the frequency of whatever mode is equal to the number of modes times the fundamental frequency F1. That guy. And then we can also talk about these as harmonics. So these different harmonics, and you might have heard of these in music, are the first harmonic means 1 bump. That's the fundamental frequency. The second harmonic would be 2 bumps. The third harmonic is 3 antinodes. The fourth harmonic is 4 antinodes. And that's a multiplier of the frequency times the number of modes. So the fourth harmonic would be the fundamental frequency times 4. All right, so let's do a little practice and identify some harmonics on a string. A 2.5 meter long string vibrates as a 100 hertz standing wave with nodes at 1 meter and 1.5 meters from one end of the string, and no points in between these two. Which harmonic is this? What is the string's fundamental frequency? And what is the speed of the traveling waves on the string? Okay, so I'm going to start by drawing a little diagram here. I know that I have a 2.5 meter long string, and it's tied off at 0 and 2.5. And then I know that I have nodes at 1 meter and 1.5 meters. So that means there has to be a bump right there, right, at 1 and 1.5. But there's no nodes in between those. So that means each bump has to take half of a meter. So if a bump takes half of a meter, and I'm at 1 meter right here, then the next one should be half of a meter, like that. And that leaves me with one more space for another half meter bump right there. From 1.5 meters, another half meter away from that would be at 2 meters, and this would be 0.5 meters. So then I'd get another antinode right there, and then a last one that fits in between 2 and 2.5. So this is the 5th mode, the 5th harmonic. So this is mode equals 5. All right, so what was the actual question? Which harmonic is this? The 5th harmonic. Good. Okay, so this is the 5th harmonic because it's 5 bumps. What is the string's fundamental frequency? Okay, so the fundamental frequency, I can use that F4 or F5 equals 5 times F1, and F5 is 100 hertz. So this F5 equals 5 times F1, and F5 is 100 hertz, equals 5 times F1, and I want F1, the fundamental frequency. So divide both sides by 5, and that gives me F1 equals 20 hertz. So the fundamental frequency here is 20 hertz. And then what is the speed of the traveling waves on the string? Okay, so for the traveling waves on the string, I know that wave speed equals wavelength times frequency. And I think I'm going to do it just based off of this diagram. So the wavelength is 1 meter, because I get 2 bumps in 1 meter. So the wavelength here is, nope, not 2, 1 meter, times the frequency was 100 hertz, gives me my wave speed. 1 times 100 is 100 meters per second is the wave speed. And there we go. All right. So speaking of strings, let's talk about some different instruments. And actually, we're going to come back and do different instruments in part 2. So we're going to pause there, and I will see you again in just a few seconds.